This video will concentrate on Euler circuits and paths, which are a subject inside of graph theory. So first of all, what are they? Well, I mentioned graph theory. It's not algebra graphs, or y is x squared, for instance. Instead, we've got some vertices and we've got some edges. In the picture that I have here, the lowest square, the A, B, C, and D are going to be your vertices, and then the straight lines connecting them are going to be the edges. Now, in graph theory, edges could be a curved line. That won't matter. I mean, you could even do a little curly curl within them. It's just that one end of an edge is a vertex, and the other end of that same edge is another vertex, or actually sometimes you can connect a vertex to itself. But what about the Euler circuit and path? I mean, this is just I've just talked about this as an ordinary graph, but what do I mean by Euler circuit? What do I mean by Euler path? Well, an Euler path is anything where you can start at a vertex, start moving around, like I can go from A to B by traveling along this edge, and you can do so in such a way that you use each edge exactly once. That would be called an Euler path. Now, if in addition you end up at the same place you began, that's an Euler circuit. So paths may or may not end up at the same place you began. The only criteria is every edge is used exactly once, and a circuit does start in the same place, and every edge is used exactly once. And this I gave you, this picture, this graph is very simple. A to B, B to D, D to C, and then C to A would be an Euler circuit. Also, it's an Euler path. Okay, so do all the graphs have one of these circuits inside of them? No. What's required? Well, it needs to be connected. I mean, certainly if you're going to go from point A to point D somewhere in the process, you've got to somehow be able to connect them. So connected just means any 2 points, there is something that I can go from the beginning to the end, some way to go from one point to any other point. Now, assuming it's connected, then if 2 or no vertices are connected with an odd number of edges, then you have a path. So looking back here, the A had 2 edges, the B had 2 edges, the D 2 edges, the C 2 edges. So as criteria, we have no vertices have an odd number of edges. All the vertices were even. None of them were odd. Okay. And then I have this further thing. If there are no vertices, you can have a circuit just like I had in that picture. And if 2 of the vertices are odd, you can do a path. You would begin at one odd and you would end at the other odd. And why is this even bit? Because really, if you think about it, you are entering and leaving a place. Like, so I go from A to B and then B to D. So that requires 2. Now, in a more complicated graph, I might go A to B, B to D. I might come back again to B, and I might leave B another way. And that would just be 4 edges that connect with B. But yeah, if you're going to enter and leave the same place, you need an even number. 1 to come in, 1 to go out. If 2 of them are odd, since you're just leaving one of them, but not coming back in a path, for instance, you just, and here it doesn't work with this picture, but just imagine, if you're just going to leave A and you never come back to A, I don't need 1 path. And if I started A, sometime later come back to A, and then leave A again, but never come back, that's 3. So yeah, if you begin in a place and do not end at the same place, you're going to need an odd amount. And likewise, the ending vertex, if you do not start at the ending vertex, the ending vertex needs an odd amount. Okay, moving on. So this is a problem that came up, and I've put it in stylized and instead of the original thing, but there was a city called Konigsberg, and its residents would walk around the city and wonder, can I get from point A to point B to point C to point D using bridges? You see, A and D were the north and south side of the city, and there was a river going through the middle. B and C were islands, and so they had these bridges. You had one bridge going from the north side to the westernmost island, one bridge going from the south side to the westernmost island, and then going to the eastern island, you had two bridges each. So from the north side to the easternmost was two. From the south side to the easternmost was two. Also, the two islands were connected to each other by one bridge. Okay. And they asked, can I start someplace in the city? Take a walk on a nice sunny day. Just walk around the city and travel each bridge exactly once and end up where I started. Now, A was actually a whole big stretch of land, but as far as the bridge is concerned, this part north of the city was the same as that part north of the city. So the mathematician who studied this just kind of shrunk the north side down to a single point. And that island, he shrunk it down to a single point. And this island shrunk to a single point. And the south side got shrunk to a single point. And he asked about this. Now, from what I've shared with you already, you have probably already started counting. And you notice that the B here has 3 edges, so that makes it odd. D has 3 edges, so that makes it odd. We're allowed to have 2 odd edges only and have a path, not a circuit. These people were actually looking for a circuit. But let's continue. C actually has 5 and A has 3. Actually, every single one of these have odd. So the answer was no. They could not start from 1 and end up where they could not start at one place, walk around the city using each bridge exactly once, and end up where they started with. They couldn't even end up at a different place using each bridge exactly once. Now, okay, if you have a graph that is not Euler, can it be made Euler by adding extra edges? Yes, it can be. What you do, and I've done this here, is you find anything that's odd. Now, I had choices because all 4 of these were odd, but find 2 of these that were odd and just put another path there. And, so I put in my orange path, and that now made A and B even. I added 1 more. A used to have 3, A now has 4. B used to have 3, B now has 4. And, but C and D are still odd, and I wanted a circuit, so I wanted all of them to be even, so I added 1 more even. And now C and D both have something. Now, besides just recreational, this could be of use in a bus path. Suppose the city wants to plan a route for a bus, and they have 4 places that they know will be that lots of people want to be picked up from or dropped off at. And they're planning on going down these streets, and maybe there's 2, actually originally, let me back up here. Originally they're just saying, I'll go straight from here to here, straight to here. But they know between C and A, there's usually some people around here wanting to get on the bus, and there's usually some people around here. So they're planning on taking both paths. And, from D to C, they're planning on taking both paths. and they're planning on going along this section of road 2. So they're looking at this and they're saying, can it be done? Where I'm not going to waste time coming back along a road that I've already traveled along until I've gone along all the roads I want to travel. And as it is here, no. You're going to have to, if you want to visit all these roads, 1, 2, 3, 4, 5, 6, 7 roads, stopping at these 4 places, some of them you'll have to backtrack on before you get to the other, before you complete all 7. However, if I were to add an additional route that connects A to B and an additional route that connects C to D, then I could do it. And here is one such route at the bottom. And the way we usually write these, start at A, go to B, either one of those 2. Then I have going back to A again. Okay. Then I have going to C, and you can trace it up. And you'll, if you do, you'll find I've gone through everything exactly once. And then after that bus finishes that route, I can just repeat it all over again. But okay. I hope you enjoyed this video.